on 0.00055 AMU. So you can imagine that if the atomic mass unit is 1/12 of the mass of a carbon-12 atom, then by definition, one atom of carbon-12 weighs 12 AMU. And I just love this GIF. So the reason I put this in is I was kind of imagining that this ball is an atom of some kind, which it clearly isn't. But you know, it's my little demonstration of the fact that atoms have mass and they can be a physical force when they're in motion as well. So just a little comic relief there. Think of that as an atom. Okay, back to the periodic table. Why carbon? That's a great question, and an interesting story that I don't have time to tell you, but feel free to Google it. There was a lot of debate. It didn't have to be carbon. Let me put it to you that way. That was a choice among chemists. It did not have to be carbon, but it was carbon. Okay. I mean, there were a lot of reasons for it to be carbon. And that not just carbon, but that specific isotope of carbon, right? Carbon-12. Anyway, so back to the periodic table. Let's say one of the goals of this course is for you to know how to use it, understand it, read it. So atomic number is what? It's the number of protons. And we can look at the periodic table and we can always identify the number of protons in any given element by just reading it. So for boron, it's 5, carbon 6, nitrogen 7. I'm not going to go on until I hit the end here. That would be boring. But atomic number, again, is equal to number of protons, which increases as we go across and down the periodic table. Now we have this chemical symbol, and as I'm sure you've noticed, sometimes it's a single capital letter and sometimes it's a capital letter followed by another letter in lowercase. So fine, this tells us what element it is that we're dealing with. Then we have something important to us, the atomic mass, which, as we just said, is measured in AMUs, or if you prefer, Daltons. This too, of course, increases as you go across and down the periodic table. The name itself is given, the full name itself is given on some, although not all periodic tables. You know, they come in a lot of different flavors. Sometimes you'll have the full name, sometimes you won't. You're always going to have the groups identified. Notice there's slightly different numbering conventions depending on which periodic table you're looking at. I'm going to stick with the group 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A, just for the record. That's what I'm used to. I'm an old soul. You can't teach me new tricks at this point. Okay, so now we have some clue how to read the periodic table. We're not really going to be dealing with the lanthanides and actinides, just for the record. We're not barely going to be addressing those at all. Okay. What's next? Well, we just said the atomic number defines the number of protons. So if we want to know the number of protons present in palladium, we just go here and we say, okay, 46 protons. And 46 electrons, as long as this is a neutral atom, which it may or may not be. But if we're just reading it off the periodic table, we're reading it as a neutral atom. Number of protons equals number of electrons. Does not necessarily equal number of neutrons, as we stated a moment ago. So this is where we differentiate between the atomic number Z, which represents the number of protons in the nucleus, and the mass number A, which represents the number of protons and the number of neutrons. So does anyone remember what I said earlier about the relationship between the number of neutrons to number of protons? Just kind of a little check. What did I say about that? Can we say neutrons are equivalent to the number of protons? It is variable. Is the number of neutrons ever less than the number of protons? Equal or greater? There we go. Equal or greater. Okay. So the mass number by definition is always going to be equal to the atomic number Z, because that is the number of protons, plus the number of neutrons, and this can vary. Okay, so isotopes by definition are atoms of the same element, let's just call that element X, with different numbers of neutrons in their nuclei. Ridley, you have a question? Yes, no, maybe? What? What's your question? I'm going to go on while you're composing your question. So there are ways to indicate when we write an element what the mass number is and what the atomic number is. So if we're talking about something like uranium, which has two different isotopes, actually more than that, but the two main ones are uranium-235 and uranium-238. So by definition, the mass number is on top. What is this? This is protons plus neutrons. And the number of protons is just on the bottom here. So which one of these has more neutrons, uranium-235 or uranium-238? What's the point of neutrons? Well, that's an interesting question. They have no electrical field, neutron neutral. I'm not sure I have, I mean, what's the point of the sky being blue, right? I mean, neutrons are implicated in a lot of things, in particular in radioactive decay, because it looks nice. They absolutely have mass. Their mass is more or less equivalent to the protons, as we stated before. Okay. Anyway, moving right along, as you pointed out, as you surmised correctly, uranium-238 is heavier than uranium-235. Why? It has more neutrons in this particular isotope than uranium-235. So it's heavier. Pretty straightforward. Just an example of a much simpler element than uranium-235. Hydrogen is basically a proton with no neutrons. The most common form of hydrogen, so there are three isotopes. Let me start from a better place here. There are three isotopes of hydrogen. The most common one by far is a simple proton with no neutron at all. So that gives a little bit of a lie to what I said earlier, which is neutrons are equal to protons or greater. Hydrogen is different, as we've seen in a lot of ways. It sits in this, little known area of the periodic table. We have a situation here where your typical hydrogen atom is just a proton without any neutrons. So what does that mean? Z equals A. But there are isotopes of hydrogen. There is a case where one proton and one neutron exist in the nucleus, as you see here, or one proton and two neutrons, as you see here. This is called deuterium, and this is called tritium. So these are three different isotopes of hydrogen, just to give you an illustration of what it looks like in terms of the nucleus. And keep in mind that when we talk about an element, when we say hydrogen, what do we mean? Do we mean this, or do we mean this, or do we mean this, or do we mean a mixture of all of these? So what do you think? If I said to you hydrogen, Well, I said this one is the most common. So isotopes have abundance, but if you have a sample of hydrogen, do you think it's going to be only if you have some sample of hydrogen, do you think it's only going to be one of these things? No, it's going to be all three. By definition, we have naturally occurring isotopes. So if you have a sample of carbon, it's not going to be all carbon-12. It's not going to be all carbon-14. Some atoms are going to be carbon-14, some are going to be carbon-12. Well, Rachel, you're very much on the right track, but you're getting ahead of us. That's just in terms of the mass. I'm talking about population statistics right now and imagining things on the atomic level. We're going to have a mixture of different isotopic states for our different atoms. This will allow us, Rachel, to get at a weighted average. Ridley, I think you're going to have to let go of the neutron for the moment. I mean, you're asking a lot of really interesting questions, but it's not really going to help you understand what we're talking about right now. So, but I like the curiosity, trust me. These are, that's what scientists do all the time, is they just ask really basic questions that are actually good questions. And so such good questions that I'm not even sure I would have an answer for that. Christian, so this is more on point, Christian, to what we're talking about right now. I thought all elements have the same weight. How does that work with isotopes? That's an excellent question. Because the weight listed on the periodic table is an average weight. And that's what Rachel was just referring to. Yes. So let's take a look at that. When we say carbon has a mass of 12.01, as you see here, that is an average isotopic mass. Okay? So, but for right now, actually, in talking about isotopes, we're just going to focus, first of all, on how we can calculate the number of neutrons in any given isotope, which is a very simple exercise. So, but how are we going to go about it? For example, let's say we have some sample, we have some carbon-14, and we also have some carbon-12. They can be mixed together or not, doesn't really matter at this point. So let's say and or carbon-12. Well, the first thing that's going to be constant between these two different isotopes is they're going to have the same number of protons. We've said that over and over again, right? So it's going to have 6 protons, no matter what isotope it is that we're talking about. The mass number is going to vary, but the atomic number is going to remain constant. So if the mass number of carbon is 14, the way that we can, and the mass number, again, I remind you, is protons plus neutrons. Well, we can always find out how many neutrons we have by taking the mass number, subtracting away the number of protons, and getting back to the number of neutrons. So if it's carbon-14, it's going to be 14 minus 6 equals 8. However, if it's carbon-12, well, then now our mass number is, this is protons and neutrons minus the protons equals 6. So this is 8 neutrons here, but 6 neutrons here. So let's just put this to work. This is our, these are 2 different isotopes of sodium. So you guys tell me, if this is the mass number, which it is, and this is the atomic number, which it is, how many neutrons does sodium have? 9. Simple math, right? Is there a limited number? Mohagul asked an interesting question. Is there a limited number of isotopes an element can have? I would say yes. It's certainly not going to be infinite. On average, I don't know. It varies significantly depending on the element itself. Sometimes you can have a whole bunch of isotopes. Sometimes you only have a couple. The ones that are present, sometimes you have ones that are present in truly trace amounts, and we don't even count them when we're trying to come up with an average isotopic mass. Okay, so that was the question to answer to A. We have 9 neutrons. Well, let's, for the whole thing, the question really is how many protons, neutrons, and electrons. So we have 11 protons, 9 neutrons, and 11 electrons, right? Neutral atom. What about in B? How many, just going back to neutrons, how many? We have 11 neutrons for this second isotope. Now also pay attention to the fact that for the next couple of problems, C and D, we have a new notation here. So here we're just given the mass number. How are we going to figure out how many protons oxygen has? How are we going to figure out what the atomic number is here? Same number of electrons. In a neutral atom, the number of protons is always, so for B, it's again 11 electrons. Periodic table, excellent. So let's zoom back to the periodic table here. And we're going to find out that oxygen here has 8 protons. So this is a perfectly acceptable notation, C, but let's for a moment put our atomic number down there. How many neutrons? Nine. 17 minus 8 is 9. How many electrons? 8. How many, well, you know, we did protons already. What about this way of writing? Well, once again, sometimes there's different ways to notate isotopes, and this is a very common way. So once again, for carbon, we're going to have to go back to the periodic table. We're going to establish that there are 6 protons. So 14 mass number. Minus 6 protons. Going to give us 8 neutrons, right? Okay, I think I finally have an iClicker question for us. Oh, first I have a little more to do here. So now getting back to this question of average atomic mass. If we have a 98.9% abundance of carbon-12 and a 1.1% abundance of carbon-13, clearly the atomic mass that we read on the periodic table is neither one nor the other. It must be an average, not just an average, but what we call a weighted average that depends on these percentage values. So let's just, now you might be wondering to yourself, what happened to carbon-14 here? Why is this not included? Any theories? Why are we ignoring carbon-14, which does exist? Trace amount, not lab created. Actually, carbon-14 is very much a naturally occurring isotope and is used extensively in things like carbon dating. But it is very rare in nature. It does undergo radioactive decay. It is measurable, but we're not using it, at least not here in this example. We're not using it to get at the average isotopic mass. Note that these two things basically add up. 98.9 and 1.1 do add up to 100%. So it's the trace amount thing, basically. Okay, so here's an example of how we can put this to work. We can use something like copper as an example, which is a very important element, right? We use copper extensively in wiring, and it's a very important element. very valuable and important element, but it's quite common as well, right? So let's say that we have two major isotopes of copper. One is the isotope 63, and the other is the isotope 65. The first isotope is present in 69.09%, and the other one is abundant in the amount of 30.91%. So let's make a little, this is the kind of thing where it's probably a good idea to make a little table. Copper 63, 69.09%, just so we don't get messed up when we're trying to do a calculation, right? Copper 65, on the other hand, 30.91%, and 64.9278 AMU. So interestingly, the weighted average that you use for isotope calculations are exactly what you could do for this course if you wanted to figure out your grade at any given moment in time, because you know that iClicker is 10% of your grade, and that the homework is 10% of your grade, and the exams are 60% of your grade, and so on and so forth. Exactly the same idea. But the first thing we have to do to make this work is to convert our percents to fractional amounts, which basically just means dividing them by 100. So this becomes 0.6909, and this becomes 0.3091. So what do we do once we've gone through all that rigmarole? What do we do next? Well, we basically multiply each mass of each isotope by its fractional abundance, not percent, as I just noted, and add them together in order to get the average mass. That's all there is to it. Not difficult. So we take 0.690, we multiply it by that mass, and then we take the 0.03, etc., multiply it by that mass. We add the two of them together, and we get an average isotopic mass for carbon of 63.55 AMU. This is actually reasonable. What would you expect? Would you expect the mass, the ultimate mass that you calculate, to be closer to this number or closer to this number? The first seems pretty obvious, right? Because there's more of it. This 60, almost 70% of it is so clearly, in terms of the weighted average, it must lean a little bit more towards 62.93 AMU than it does 65 AMU. And it does. So our answer makes sense. Finally, we get a clicker question. Are you guys ready? Clicker at the ready. Let me know any. Well, I'm going to start it. Let me know if you have any issues. You're going to need a periodic table here, clearly, to look up the atomic